Trail of Bits. Dispatches from technology's future.
A long time ago, Penn Jillette, the loud half of Penn and Teller, said something like, if you could predict the future to a degree even the slightest percentage over chance, you'd be working on Wall Street. You're not going to be bending spoons on television. His point was that seeing into the future, for real, gives you practical intelligence on what's coming so you can take action to prepare for it. Companies that make high-assurance software, programs whose failure means catastrophic consequences like $1 billion disappears or the rocket ship blows up on the launch pad, are adopting technologies that are a couple of years ahead of the mainstream. When you ask a Trail of Bits engineer about what's happening, you're talking to somebody who's already operating in the future. So when they tell you about their day, it's a pretty safe bet that what they're saying is something you're going to read about one day in the future.
These platforms that allow you to take out flash loans have essentially allowed attackers to call a smart contract and get their hands on hundreds of millions of dollars in funds for 10 seconds.
That's Nat Chin.
I'm a security engineer too at Trail of Bits. That means that an attacker suddenly has an insane amount of funds that they can use on a system, and if exploitable, use that money to essentially sweep the system and steal everything.
She recorded that comment about a week before what she said happened to a DeFi exchange exactly as she said it would. In the spring of 2022, we asked several Trail of Bits security engineers what they're concerned about and what they're expecting in the next 18 to 24 months based on what they see right now. Their answers were varied, but we heard a few common themes as we talked with engineers across our three main focus areas: cryptography, blockchain, and application security. One thing everyone mentioned was how the industry looks at memory-safe languages and their potential to make developers feel just a little too safe.
People say, oh, we wrote it in Rust. Rust is memory safe, so there can't be any bugs in it. Well, that's bullshit.
Opal Wright is a cryptography analyst at Trail of Bits. Here's memory safety in simple terms. If a computer language isn't memory safe, it's easier to manipulate memory as a backdoor into a system, to crash it, or worse. A memory-safe language is designed to close this loophole. There are a number of memory-safe languages: Rust, Haskell, Golang, and a bunch of others. A memory-safe language reduces the chance of an attack.
It prevents certain types of bugs from happening.
But Opal worries, many of our engineers worry, that developers have gotten a false sense of security from memory-safe languages.
Logic bugs happen.
Here's Opal again.
If you're not checking for certain conditions with the keys that you're getting, if you're not checking for the point at infinity when you're verifying a digital signature, guess what? You're still going to fail. The fact that you wrote it in Rust doesn't mean you know what you're doing.
Shake a software executive or developer awake in the night and demand to know their testing regime, and they'll regale you with stories of their testing: unit testing, static testing, even dynamic testing. Building code that's safe requires you to know what safe means. But the future of developer education is a real departure from its current meaning. Here's Trail of Bits CEO Dan Guido.
The future is about the business saying, this is what we expect the program to do. Tell me if it ever does anything different. Anything that varies from what's desired, that's a bug.
The future of testing isn't about the tools you use. It's about what you test and why. It's verification-driven testing.
When we talk about developer security training today, we're trying to teach developers how to avoid writing code that's susceptible to a never-ending and always growing list of attacks. That's impossible. The best teams go in the other direction. They tell their developers to write code and list out the specs, invariants, properties. What specifically should this code do? Then we let tools find places in the code that allow unintended things to happen. That's the future we're in.
What does your code depend on?
Here's Nat Chin again.
How do you expect a user to interact with your system?
Trail of Bits has leaned into building application invariants into testing. This used to be hard, and now it's required. We've found that these things work really well on cloud-native software because they are built in service-oriented architectures. Lots are in Kubernetes. Lots of them have reproducible builds.
This has always been the case for cryptographic code, but now we're able to do it on cloud-native software, smart contracts, layer 1 blockchains. This allows us to refocus on what's important to the business in the code.
Is it possible for a user to bypass the way in which you intended the system to be used? What are the expected inputs into a smart contract? What are the expected behavior of the smart contract? And then what's the expected output?
This concept, gathering expected inputs and outputs, is what people who care about safety do and what everyone will be doing soon. This is different from just testing or the classic advice to understand the condition of your assets. It's understand your invariants. Does your code support things you don't intend it to?
For example,
Here's blockchain team lead Jocelyn Feist.
if you have a token, an invariant could be that no user in the system should have more tokens than the system total supply.
We've all seen the consequences of failing to answer those questions. We see it with every major hack of a cryptocurrency exchange or a smart contract, which happen at an increasingly regular pace. The flash loan breach we mentioned earlier, the theft of $180 million in Beanstalk Farms tokens, this was a consequence specifically of not doing this. Nat's advice? Follow the old Soviet legal model, which basically said, that which is not required is forbidden. Verify that the things you want to happen will always happen, and the things that you want not to happen never happen.
You need to know what your code does, and you need to be able to have some, in the case of DeFi, preferably mathematical formula that you can compare against so that you can actually check that the code behaves as you expect.
Breaking programs down into smaller chunks lets you test them more precisely. That's the only way that seemingly impossible verification problems get slightly less impossible. Nat has some basic advice informed by scores of audits.
Start small. Once you have an idea of what you want to build, building a minimal product and feature set of that code base and sticking to your scope, as well as applying unit testing and fuzzing to make sure that code behaves as expected, and then audit and slowly, iteratively add new features to that code base.
It's the same thing with missing or incomplete testing.
Here's Trail of Bits CEO Dan Guido again.
People can have great tests, but we're in a world now where security testing means something a lot more formal than it used to, where instead of relying on system-level invariants like does it crash, memory on safety, you need to test for application-level invariants, logic flaws.
The clear message from the future? Consider how you assemble the software you create with an eye to writing code and its supporting documentation that's more easily testable so that you can use the right tests for the job. We're living through a cryptocurrency gold rush. Like every gold rush in history, there are certain givens, and one of those is that people move fast to get in on the action. One impact of this that our cryptography team has noted has been a shrinking of the analysis window. That is, there's been an increase in speed to market that's driven not by new technology or better practices, but by greed and worse practices. Simply put, there's a reason that it takes so much time to approve cryptographic standards. Getting cryptography right is hard.
Historically, the time between publishing some sort of new cryptographic tool and seeing it deployed in a security critical system has been a lot bigger than it is right now.
The trend we see here comes in two parts. First, investors and CEOs working on systems that leverage cryptography continue to try to push the boundaries of what is safe to mean it delivers the features we want, so it's good. Again and again, they push those boundaries until there's a catastrophic failure.
So the problem is that CEOs and other decision makers seem to only consider the upside that newer cryptography can deliver.
Trail of Bits cryptography lead, Jim Miller.
But they often don't account for the inherent risk associated with using these newer, less battle-tested protocols. This really applies to new technology generally, but the cost of getting crypto wrong can be far higher in practice.
Second, because of the dynamics of the blockchain world, when the catastrophic failure does come, it's often dismissed by those remaining standing. The company that failed did it wrong, but that won't happen to us. It's the nightly news. Bad things happening to other people. When NIST was looking to standardize its Advanced Encryption Standard, AES, they announced the candidate algorithms in August of 1998, but they didn't pick a winner until October of 2000, and they didn't publish a standard until November of 2001.
That's a 3-year gap during which there was a lot of analysis, a lot of effort put into analyzing the candidate algorithms and then eventually just focusing on Rindall, which was the winning algorithm. And even with all of that, 4 years later, Dan Bernstein published an attack on what was the standard implementation at the time.
The attack shook the industry, which scrambled to find ways to avoid this kind of thing in the future. Opal mentions that this attack is one of the reasons that, to this day, a lot of processors include certain instructions for AES.
There's a similar thing going on right now with the post-quantum standardization effort that NIST is running. The proposals were published in December of 2017. As we're recording this, it's April 2022, and it's still going. But just last month, 4 years into the process, somebody published an attack against one of the finalist algorithms, and it absolutely demolishes the security.
So a larger window, a window that's open for a longer period of time, is a responsible and good thing to have. It takes time for cryptographers to get their head around the math, around the specifics of the implementations. This isn't something you can just throw together, and yet,
unfortunately, blockchain is really shrinking that window. Things like threshold signature schemes, some of the zero-knowledge proof schemes, they get published in one issue of a journal, and before the ink is dry on the next issue of the journal, the software has been written to implement what was originally published, and it's out the door, and some cryptocurrency startup is using it to protect hundreds of millions of dollars. But I think the answer is to be conservative, to wait for analysis to happen, to give that larger window, give it a little time, wait for the dust to settle on the analysis.
And these tools, like threshold signature schemes, are so complicated to develop that lots of people find it easier to just use an existing library to get them done, rather than developing it themselves. This can be smart if it comes from a good team that knows what they're doing, but it can also make the blast radius of a bug in those libraries more impactful, because more people are using them. Opal's counsel for those in the blockchain business, what the best companies do, is do good math.
I think at some point in the next couple of years, we're very likely to see somebody making $1 billion bet on a piece of math that turns out to suck. If you're doing cryptocurrency, if you're doing these sidechains, if you're doing zero-knowledge systems, if you're doing multi-party computation, if you're doing these threshold signature schemes, you need to have experts on your team who actually know what they're doing.
Because even though these tools aren't new, and they've been the topic of extensive academic study for years, people are now translating them for the first time into software. Translation mistakes are popping up all over the place.
There's quite a lot of effort that's put into writing and peer reviewing these papers.
Here's Trail of Bits lead cryptographer Jim Miller.
And although mistakes do happen from time to time, we can be reasonably confident in their correctness. But this peer reviewing is largely from a purely theoretical perspective, making sure things like cryptographic security proofs are correct. But they're going to focus less on things like missing implementation details and misleading notation. They're not implementation guides, they're theoretical protocols. And translating theoretical protocols into software is really hard.
And we need good math now more than ever, because applications are getting more complex. And since we're talking about the rush to adopt software quickly, with narrower and narrower windows for testing, let's turn to our blockchain team. All those conditions are business as usual in the blockchain industry.
My name is Jocelyn Feist. I'm a principal security engineer at Trail of Bits. We are seeing two types of category on smart contract. The first one are related to issues that are common flaws. Things like reentrancy or unprotected upgrade.
The fact that reentrancy is still making its way into smart contracts is a problem similar to what Wendy Nather has called the security poverty line and what Trail of Bits CEO Dan Guido calls security haves and have-nots.
We're seeing a bimodal distribution of people in the blockchain space. On one hand, there are teams with 2017-style integer overflows, and on the other, there are teams with extensive properties and verified code. There's no one in between.
The difference between the haves and the have-nots in this case is 5 years of progress.
Those mistakes were very easy to make because of the nature of Solidity and the nature of a language that doesn't really prevent you from making these mistakes.
Now, this isn't some academic statement or compliance-driven best practice. Those living in the past are forgoing hard-won and often painful lessons. Especially with smart contracts, which don't have system-level invariance, it's not just a matter of, say, fuzzing and it's all good. You can't use crashing in a smart contract as a proxy for a bad outcome. It's much more about specifying what good looks like. We've just heard from several software security engineers about what they see as trends, so it's worth taking a moment to consider the high-level message they've given us. In the next 2 years, making mainstream software will become dramatically more complex. This isn't just about the high-assurance stuff. It's all software. We all expect our code to do more, and that functionality comes from modern techniques that allow us to include ever-increasing external services and libraries. We've passed the time when engineers could eyeball their code or run simple unit tests to see if everything works. And let me be clear, we have no skin in this game because we don't sell testing gear. You need all the testing, regardless of whether you ever do an audit with us or anyone else.
You don't need static analysis or dynamic testing or fuzzers.
Dan Guido puts it like this.
You need to know what your code should do, and you need to build it so you can test for that. Then, applying the correct testing technique is easy. I think we really need to define what kind of testing we're talking about. This cost of testing versus not testing thing will not land. People test their code today. They will insist they do. The difference is test against what, and then test how.
We have one more idea that our engineers brought up when we asked them to look into the future: compilers. We've already talked about writing code. We also need to talk about compiling it. And we can't say this too strongly. The new ways of compiling software are the future.
Compilers are used every day by every company around the world for taking their source code and turning it into machine code which runs on servers. My name is Peter Goodman, and I'm a staff engineer at Trail of Bits.
Peter is looking really closely at compilers because the world of compilers is changing fast, too.
I do a lot of work on where compilers are today and where compilers are going in the future, because I'd say we're on I'd like to think like a 20-year cycle of compilers.
His look at the last 20 or so years of compilers starts with the GCC, the GNU Compiler Collection, which most agree is an excellent compiler suite, very popular in the Unix and Linux open source worlds.
GCC was always thought of as this beast of a compiler in some ways. Like, it's open source. Everyone can edit it, everyone can look at it and stuff. But it always had this reputation of being challenging to modify.
In the early 2000s, LLVM came along. Oh, one thing about these names. I said GNU before, which famously is a recursive acronym that stands for GNU's Not Unix. In much the same way, LLVM really just stands for LLVM now because its early name, Low-Level Virtual Machine, confused everyone since they really weren't describing what most people think of today as a virtual machine. Don't get us started on names. So LLVM, born at the University of Illinois, evolved to kind of fit behind the GCC. Eventually, it got adopted by Apple, which now uses LLVM as the primary compiler for all its hardware and software. This was partly because GCC came with licensing restrictions that required a company that extended GCC to contribute that extension to the open source community. For organizations looking to build out new competitive advantages, that was a non-starter. The LLVM licensing restrictions are far more lenient.
So somebody like Apple could start working on compiler backends that would target their custom hardware that they hadn't told the world about yet. And they would never need to reveal any of this stuff until suddenly the new iPhone is released. And it's like, oh, there's this A4 chip. Surprise.
That mix of commercial and academic sensibilities led to dominance.
It democratized compilers. Suddenly, there was this compiler technology that academics could get behind because it was created by academics and it was open source. Industry could get behind it because they could develop it for their own niche architectures. You had this huge investment from academia and industry just pushing this technology further and further and further and further.
Today's compiler technology operates at a level that's somewhat similar to where the machine is operating. So it's able to do very good optimizations that match what machines can do.
We need a representation that's closer to the source code. And then maybe we need another representation that's somewhere in between the source code and this machine representation.
He's talking about intermediate representation, ways that source can be represented in a way that is somewhere between source code and the machine code. Imagine a spectrum. The source representation is close to the language itself. You'd want to represent the language constructs in a way that's close to how the language itself represents them. So LLVM is very close to the machine, representing things in terms of instructions. But now, let's introduce some other dialect, something that's perhaps close to a simplified C. It has some structure, but it doesn't have all the bells and whistles of the original language. That would be an intermediate representation. And Peter thinks that's where everything is headed.
I think the future is a technology called MLIR. It stands for multi-level intermediate representation. And it's hugely popular in the machine learning industry for optimizing all their workflows and computations. But I think it's a sort of future general purpose compiler technology system or framework as well. It's got a lot of investment from academia and industry.
Big programs have traditionally meant tons of work to analyze, so the shift to MLIR means that this analysis will become simpler. This will empower developers.
Is it the best thing there is? Is it the best way of representing code? Maybe not. But what it has going for it is exactly what LLVM had going for it over the last 15 years, which is it's got a lot of momentum from academia and industry.
The people who worked on this podcast are Emily Havik, Chris Julin, Dan Guido, Opal Wright, Nat Chin, Henrik Broden, Frederick Dahlgren, Jocelyn Feist, Peter Goodman, Jim Miller, David Pecora, and hi, I'm Nick Selby. I'm the director of the software assurance practice at Trail of Bits. Chris Julin made our theme music. Trail of Bits helps secure some of the world's most targeted organizations and devices. We combine high-end security research with a real-world attacker mentality to reduce risk and fortify code. We believe the most meaningful security gains hide at the intersection of human intellect and computational power. Learn more at trailofbits.com or on Twitter @trailofbits. Dan Guido's Twitter account is @dguido, and I'm @fuzztech.